Wednesday, January 22nd, 2014.
Okay, good morning everybody. This is the second discussion for 555 for those of you that you are from another class. So let's get started. So today we're going to present some problems on queuing theory. I hope you have seen the introductory material that we posted last week. It's on then available. Please make sure you review this material as soon as possible because you will see these things in the exercises that follow, okay? Let's start with the first problem. A company has 4 private telephone lines connecting 2 of its sites. Suppose that requests for these lines arrive according to a Poisson process at a rate of 1 call every 2 minutes. And suppose that call durations are exponentially distributed with mean 4 minutes per call. When all lines are busy, the system delays, which means it queues the call requests until a line becomes available. Find the probability of having to wait for a line. Also find the average number of calls waiting in the queue and the mean waiting time in the queue. Is the problem clear? So we have Poisson arrivals, we have 4 lines, we have 1 single queue, and we have 4 lines serving the calls, right? And it's given what is the arrival rate and what is the service rate, or basically the call duration, which for us, if we translate it to queuing theory terminology, this is going to be the service time, right? So with Poisson arrivals, exponential service times, and 4 lines or 4 servers, what's this queuing model? Any ideas? Have you seen queuing theory? How many people from here have seen what an MM1 is? Only 3. So the rest don't know what MM1 is? Have you seen the material we posted last week? Okay, so here we have some issue. Guys, everything that I'm going to present today is related to the material we posted. Okay, so please review this material carefully because it has definitions, it has things that the professor mentioned in class. You have seen basic things, right? The professor did an exercise last week on some queuing system, right? So continuous time Markov chain, basically. Okay, so I'm not going to do any proof of queuing theory basic results here. We're going to use those results for our exercise. So let's get started here. Problem number 1. From what is described in the problem, we have that average arrival rate equals lambda by definition, and this is 1/2 calls per minute. Okay? And also it's given from here in the problem that the durations are exponentially distributed with mean 4, which means that the average service time, as we call it in queuing theory terminology, equals to 1 over me, because it's time versus service rate, and this is equal to 4 minutes per call. All right, so, and also we have that, we have 4 lines, meaning the number of servers is 4. Okay. Equals C. That's how we call it, okay? How we represent the number of servers. This means that the system can be modeled, as I said, as an MM4. The system can be modeled as an MM4. What is the first M here? It represents Poisson arrivals, right? The second M is exponential service times. The third number here is, we represent in general case as C or as M, and it represents the number of servers in the system. Okay, perfect. So now we can use the results that are posted on DEN on a presentation about introduction overview of queuing theory. So I'm going to use formulas from there. If you don't understand something, go back and check it out. And also, you can either go in 2 days. Professor will hold 2 extra lectures presenting this material and most likely doing proofs and stuff. Okay, so please make sure you attend those extra lectures. They are very important. So from the MM4, we know that the server utilization. Why we present server utilization here? Because we need it in the calculations. It's represented as rho, and this is equal to lambda over C times mu. You saw that yesterday, right? So C is the number of servers. So this is 1 over 2, 4 times 1 over 4, and this gives 1 over 2. So 50% of the time the server is busy. Okay, so let's make a diagram. I think it's going to be much easier to understand what's happening of an MM4 system very quickly. I hope you can do that. With the state here in this continuous time Markov chain, we represent the total number of packets in the system, right? So we have 0, 1, 2, till 5. Sorry, it's not till 5. It's it goes up to infinity potentially. But we have 4 servers, which means something changes when we have maybe I need to represent all the states. 3, 4, 5, that's better. Okay, so what's happening here? What is the arrival rate? What is the rate we go from 0 to 1? All the arrival rates are lambda here, right? So we know that from a state to go to the next state, which means to add a customer to the system, we go with rate lambda because there is an exponential that fits the traffic, Poisson arrivals, okay? That fits our queue with traffic, or our system better. What is the rate we go from 1 to 0? What is 1? 1 means there is one customer in the system, right? So it's going to be mu, right? Because we have only one exponential counting. It's how much time it's going to take for him to be served, right? What about the rate 2 to 1? 2 mu. Same here, 3 mu, right? Same here, 4 mu. What about 5 to 4? 4 mu, why? because we have 4 servers, right? We don't have more than 4 exponentials, right? Do you agree with that? Make sure you understand these details and make sure you understand the fundamental theorems that basically create this result over there, which means the minimum of n exponentials or, these type of things. Or what happens if you have a sum of Poissons. You will see this in the review, but those are fundamental results that we use all the time. Okay, so now probability of having to wait in the line is the first question we need to answer, right? Find the probability of having to wait in the line for a line in the queue, for a line to be available, and that's the first thing we need to find. Having to wait in the line, in the queue, is equal to can you translate it into probability of being in some particular state? In which state we should be in order to wait? 4? Only 4? 4, 5, 6, and etc., right? So it's probability of n greater or equal to 4, because if we are here or above, then we need to wait. Because all servers are busy, right? We have 4 customers in the system, a new arrival comes, it has to wait. Okay, good. So for that, this is a very well-known formula. It used to be very popular when they had all these old telephone systems, and it was showing what's the probability. Basically, you have to wait. All the lines are busy. And this is called Erlang-C formula. Erlang-C. It's a complicated formula, but there is a short representation for that. We represent it as C, the capital C, small c, the number of servers, lambda, comma, mu, which is the service and the arrival rate and the service rate, or you might see it as lambda slash mu, lambda over mu, which is the another way, the row anyway. And this is equal in our case to C for 1 over 2, 1 over 4. Okay, so now we're going to go ahead and present the formula without proof, because it's going to take a while to derive those formulas. So C lambda comma mu equals to, I hope you can see that, it's lambda over mu to the power of C factorial, and then we have lambda over mu to the power of C factorial plus 1 minus rho sigma from 0 to C minus 1, which is the number of servers, minus 1, lambda over mu to the power of n, here the index, over n factorial. Don't tell me that this is not easy to remember, right? So, of course, we're going to use it without proof here. And okay. So we just need to substitute now and find what's the number, right? So by substitution, we get that Pn greater or equal to 4, this is n, is equal to 4 over 23, and this is equal to 0.17. Any questions so far? Okay. Now let's go to the next question. The next question is find the average number of calls waiting in the queue. Average number of calls waiting in the queue. In queuing theory, you'll see two categories of averages. One is the average something, like average number of customers waiting in the queue and the average number of customers in the system. Two different things, queue and system. The difference is that we include the customers being served. And this is not a difference by one. If the server, we have many servers, the difference is big, right? So we'll differentiate those two cases, and then we'll have the same for times. Waiting time in the queue, right? And the time in total until you are served. Okay? So let's see what we have here. Find the average number of calls waiting in the queue. We represent that as, it's an average, we represent as an expectation. In some books you might find this expectation being omitted by definition. They say, okay, I'm representing this straight with an NQ and this is an average. Although it looks like a random variable, in some cases like Ross' book, probabilistic models, they represent it as without expectation for, convenience. Okay, this is the average number of calls waiting in the queue. And this is equal to, from the results of MM4, rho over 1 minus rho, excuse me, C4, 1 over 2, 1 over 4, from the Erlang-C formula. And this is equal to 4 over 23. Let me see, because I don't like something here. Yes. And then what is the average? The next question is what is the average number of, the mean waiting time in the queue. We want the mean waiting time in the queue. We represent that as W, which is the average waiting time in queue, and this is equal to, do you remember a law called Little's law? Have you heard of that? Basically, no. It gives us a relationship between the queue length, the waiting time, and the arrival rate. All right? So in this particular case, we use a result like this. It's expected number of NQ, number of calls waiting in the queue, over lambda. And this is 0.34. All those are well-known relationships. I guess you need to make sure you have seen those formulas. Okay, and the mean waiting, sorry, what is? Yes. And also we'll give another result here, which is the expected N, which is the average number of calls in the system. Expected N is equal to average number of calls in the system and this is equal to expected NQ plus lambda over mu. Where this is coming from? Basically, this is the number of customers in the queue, and this is the ones being served, right? Okay. And this is approximately equal to 117 calls. Okay. Just this is informative here. We don't ask this question, but yeah. So any questions? How many people are lost completely? Just be honest, guys. You have time to refresh this material or to read for first time anyway. Okay, so that's good. Nobody's lost. If you have questions, feel free to interrupt, right? Okay, let's go to problem number 2. Suppose that two types of packets arrive at a queuing system according to independent Poisson process of rate lambda over 2 packets per minute. Both types of packets require exponentially distributed service times of average rate mu packets per minute. Okay, we have two types of packets. Type 1 packets are always accepted into the system, but type 2 packets are turned away when the total number of packets in the system exceeds k. Some parameter k, all right? First question is sketch the transition rate diagram for n, where n is the total number of customers in the system. And B, find the steady state PMF of n, probability mass function. Make sense? So we have a queuing system, two types of arrivals. One goes always in, the other is low priority kind of. So if we are busy, if the queue is full, which means if we have a capacity, let's say, of k, above k we are dropping all the arrivals that are coming from, the type 2 packets, basically. All right, so problem number 2. I'm going to just draw a diagram. We represent a queuing system usually like this. This is the service rate, this is the arrival rate, lambda over 2, this is type 1. And then we have another arrival type 2, but it can go out if n greater or equal to k. And type 2. Do you agree? Okay. So what do we know from the problem? That we have two Poisson processes feeding this queue with a rate lambda over 2. So from probability theory, what is the sum of two Poisson processes? Poisson. They are independent Poisson processes. We sum the two lambdas, right? It's a Poisson with rate, the sum of the rates. Very fundamental result. We're going to use this here. Okay. So the transition, in the transition diagram, we said that n represents the number of customers in the system, and we need to draw that. So if n is less than k, then what is the total arrival rate? It's lambda, sum of two Poissons, okay? if n is greater or equal to k, what's happening over there? Total arrival rate in the system is lambda over 2. Only one type of packet, only packets of type 1 are accepted. Okay, good. So now I guess we can easily draw the diagram, and let's do that here. State 0, state 1, state 2, k plus 1, k plus 2. All right? What is the rate we go from 0 to 1? Anybody? Lambda, right? Drawing this diagram is very, very important, because you can, if you know the tricks how to do the balance equations, you can solve any Q. Believe me, you'll see. So the arrival rate is lambda. The rate will go from 0 to 1 is lambda 2. And from 1 to 2, same thing, right? Lambda. And this is also the rate we go from k minus 1 to k. This is lambda. This is mu. This is mu. Mu all the time here. We have one server, right? Okay, so what is the rate we go from k to k plus 1? Lambda over 2. Same for all the states above k, right? Lambda over 2, lambda over 2, and so on and so forth. Now, do you remember the tricks to calculate the balance equations, as we say? How do we do it? We just cut the chain in 2 halves, and then we say lambda times the probability of being at state 0 is equal to mu, which is the rate we go out of state 1, times P1, right? Which gives, if we solve in terms of P1, lambda over mu times P0. You should be able to do this and fast, okay? This derivation here. Lambda times P1 from this cut here, lambda times P1 is equal to mu times P2. Mu times P2, and this gives P2 is equal to lambda over mu P1 is equal to lambda over mu square P0 if we use this result here. So we kind of guess now what is the generic formula until at least k, state k. We have two in the exponent here. So we will generalize pk is equal to lambda over mu pk minus 1, and this is equal to lambda over mu to the power of k p0. Okay? That's all the probabilities, the balance equations till state k. What's happening above that now? Above that, meaning here, in this cut, we have lambda over 2 times pk is equal to mu times pk plus 1, which gives pk lambda over 2 is equal to pk plus 1 times mu, which implies that pk plus 1 is equal to lambda over 2 mu times pk, and this is equal to lambda over 2 mu times lambda over mu to the power of k p0. We use the previous result. Okay, good. So next step. what is the generic case from K and above? We can kind of generalize. We can say that for all J greater than K, do you recognize the symbol? For all J greater than K, the formula is Pj is equal to lambda over 2 mu Pj minus 1. Now, how do we count the states here? We want to use the result for Pk. We want to have, instead of having P0, the first step is to use Pk and then substitute, right? Or you can do it directly if you want. So we need something like that. Lambda over 2 mu to some power here times Pk. So what is this power here? It's what? J minus K, perfect. J minus K. It's like we start counting from here, right? This is 1, 2, 3, J minus K. This is how to the right we are starting from K. Okay. And we continue the derivation here. What this is equal to is lambda over 2 mu J minus K, and then we substitute Pk, right? We have Pk is equal to that. Lambda over mu to the power of K, P0. Now it's up to you what kind of, calculations you want to do. If you want to merge the exponents, if you want to take the 1 over 2 to the power of J minus K out, we can do many things. I'm going to present just one way of doing it. And what I mean by that, what do we need to find over here, first of all? We want to give the PMF, right? Find the steady state PMF of n, which means we need to give a formula of calculating every probability. Now we expressed everything in terms of P0, but nobody knows P0 so far. So we need another equation to add to the system of equations in order to be able to solve and find all the unknowns. And that's the very trivial equation that the sum of all the probabilities is equal to 1. Also, summation from j equals 0 to infinity of Pj, right? Why we say infinity? Nobody said that the Q has limited capacity, right? We say that we are dropping arrivals, but nobody said that it's limited, the Q length. So the summation of all these infinite probabilities is equal to 1, and if we substitute, this gives what? Let's go here. We need some results from here, I guess. This is summation. We're going to break this into two parts, right? Summation from j equals 0 to what? 2k. Let's do it first like this. Lambda over mu to the power of j plus summation from j equals k plus 1 to infinity this is the formula, right? Lambda over 2 mu j minus k lambda over mu to the power of k. Now we can observe that thank you guys, very good cuts. I got excited with the summation and I forgot it. Okay, P0, of course. Now, as we can observe here, we need to use basically geometric series, okay? You can use whatever you want. I'm going to just give you the geometric series, first of all, here. Just to do you remember the formulas? Everybody? Perfect. So we can observe that we can move this guy here, or move basically the summation from here from 0 to infinity, because if we put, let's say, this guy from 0 to infinity and this guy till k minus 1, then what happens here? From 0, we have, sorry, not from 0, if we put here from k to infinity instead of k plus 1, right? Then the exponent here becomes 0, which gives basically this formula here. So those two guys become equal for k equals 0. So this can be written as summation from j equals 0 to k minus 1 lambda over mu to the power of j plus summation from j equals k to infinity of lambda over 2 mu to the power of j minus k lambda over mu to the power of k. Do you agree with that? Because this guy, for k, j equals k, this guy vanishes. So it's like we moved this guy here. Huh? Do you agree? Okay. So with that said, now we can use the trivial form of the geometric series, which here it has till k minus 1, and it gives an exponent of k in the fraction. You said you remember. Do you remember? Yeah, let's do it together. Okay, I'm kidding. It's P0. What is the geometric series? It says that the summation of some number to the power of j is going to be 1 minus this to the power of j plus 1 in the general case, or if it's still j minus 1, sorry, k minus 1 is going to be to the power of k. So it's going to be 1 minus lambda over mu to the power of k. Perfect. One term. Very well. And then we have the other term, it's P0. This is independent of the summation. Do you agree with that? It's to the power of k. It's independent. It's constant for us. So this goes out and it becomes lambda over mu to the power of k, and then we have the other geometric series, which is, let's see, what is this exponent here? We start from k, which for us is from 0. That's why we did it basically, the transformation, right? It's from 0 to infinity. The upper bound doesn't change, is infinity. So this is going to become 1 over 1 minus c, right? Not c, I mean, you know, the parameter inside the exponent, which is 1 minus lambda over 2 mu. Do you agree? Okay. So this implies that P0 is 1 over all this thing. 1 minus lambda over mu to the power of k over 1 minus lambda over mu. Yes? Oh, thank you. Lambda over mu to the power of k over 1 minus lambda over 2 mu. Everybody agrees? Okay, guys. So that's it about this problem. If you don't have questions, we can move to the next one. Take a look and let me know if you have questions before I switch. All right. So problem number 3, the last one. Packets arrive at a service node according to a Poisson distribution with mean arrival rate of 1 packet every 3 minutes. The service time is an exponentially distributed random variable with mean of 2 minutes per packet. The first question is, what is the probability that an arriving packet will have to wait? Okay, a probability an arriving packet have to wait. And then we'll continue with the next while we're solving it to save time. Problem 3. So we have, what is the average service rate, average arrival rate, sorry? Equals lambda equals what? 1 packet every 3 minutes, right? So it's 1/3. Packets per minute. The units are very important. It might change if something is expressed in other units, arrival versus departure. So be careful with that. Average service time. As you see here, we have rate versus time. That's why one is lambda and the other is 1/mu. And this is equal to what? 2 minutes per packet. Okay. What kind of queuing system is this? What do we have here? We have Poisson arrivals, we have exponential service times, and we have a service node. MM1, right? So this is an MM1. So the probability of waiting, which is the first question, probability of waiting is equal to the probability of what? When do we wait in the system with one server? Server is busy. Probability of server is busy. And this is equal to, do you remember? Good. It's rho over 1 minus rho, right? Or 1, or no? Sounds like a Q length or something else. What is that? Is it the server utilization? Server is busy, right? So this is equal to server utilization, and this is equal to rho, meaning lambda over mu, which is 2/3. You were close to that. Okay, so that's the first question. What is the average number of packets waiting in the queue? Average number of packets waiting in the queue. We represent that as n sub q capital, and this is equal to, there are many ways. I don't know, somebody said lambda square, blah, blah, blah. If you define rho as lambda over mu, which is the case here, you can see many different variations of the same form, right? If it uses lambda or rho. So I'm going to give you the rho-based formula, which is rho square over 1 minus rho, and this gives 4/3. But feel free to use any other form if you know. By the way, as I told you, those formulas, you don't have to remember all of them. Just remember some basic ones, and then use Little's law. Okay, to go from lengths to time and vice versa. Okay, Q lengths. The third question is, the network administrator plans to add another server when he becomes convinced that an arriving packet would expect to wait on average at least 5 minutes before being served. At what average arrival rate will this occur? For this arrival rate, find the average delay and the average number of packets in the system, both waiting and being served. So the question here is, the administrator wants to add another server when, for some lambda, we're looking for this lambda that makes the system so busy that somebody has to wait for at least 5 minutes. Okay? So our kind of question here is, what is lambda? What is this lambda that creates so much traffic in the system? Such that somebody has to wait for 5 minutes. So average waiting time is equal to expected W, that's how we represent it, is equal to rho over 1 minus rho times 1 over mu. And this gives 5. Okay? So, what is the rho in this case? As I said, lambda is a new lambda now, a lambda prime. So, our rho is a new rho as well. It's not the previous one. Maybe I should represent it as rho prime here. So, rho prime is equal to 5 over 2, 1 minus rho prime, which gives rho prime is equal to 5 over 7, equals to 7143. Do you agree? What did I solve here? We want the average waiting time to be 5 or more, meaning we want to see what is the transition point, right? For which lambda we will start waiting for more than 5 minutes. Do you agree with that? So the expected delay, I'm taking equal instead of saying greater or equal to find the minimum lambda that satisfies that. So in this case, R prime is going to be that much, which gives that R prime is equal to lambda prime over mu, which is equal to lambda prime times 2, and this is equal to 0.7 from above here, which gives that lambda prime is equal to 0.357 packets per minute. Okay, and do you agree with that? So, for this arrival rate, lambda prime, what happens? Average delay, do you see? Okay. Delay in the system is equal to expected T, and this is equal to expected W plus expected S. Those are standard notations here. This is the service time, right? As we said, expected W is 5, because that's what the question says, 5 or more. And 2 is the 1 over mu. Do you agree? Which gives 7. So we answer to the question, for this arrival rate, find the average delay and then the average number of packets in the system. So now we want to find the average number of packets in the system. Any questions? So the average number of packets in the system is expected N, and this is equal to lambda prime expected T. Sounds like Little's law here, or maybe not. Maybe yes. 357 times 7, and this is 2.5 packets. Yes. Just the last thing, very quickly. At what average arrival rate will the system become unstable? That's very trivial. It's an MM1 when an MM1 system becomes unstable. System becomes unstable when rho equals 1, which means lambda equals mu equals to 0.5 packets per minute. Do you agree? That's a basic definition. Come on, everybody knows that. Don't tell me that you don't remember this result. Okay, any questions, guys? If you have questions, let's talk then in the break. Okay, thank you very much.
And this concludes EE 555 discussion on Wednesday, January 22nd, 2014.